All right, let's just jump right into it. Welcome to today's explainer. We're going to be exploring the fundamental chemistry of everyday life, specifically acids, bases, and salts. You can kind of think of this whole topic as a microscopic tug of war happening all around us. It's this invisible battle of chemical forces that ultimately creates the incredibly stable materials in the world we interact with every single day.
Here's how we're going to break it down today. First, we'll officially meet acids and bases. Then we'll dive into strength, concentration, and pH. After that, we'll look at the sheer power of their reactions, and we'll wrap up by exploring everyday salts and compounds. So let's kick things off with Section 1, Meet Acids and Bases. Right off the bat, there is this core chemical duality that dictates so much of our physical world. On one side, you have acids. If you've ever bitten into a raw lemon, you know exactly what I'm talking about, that signature sour taste. Chemically speaking, acids release hydrogen, or H+ ions, when they're in an aqueous solution, and they'll actually turn blue litmus paper red. But then, on the flip side, we have bases. These have a distinctly bitter taste. Think of things like baking soda or even soap. And they do the exact opposite, turning red litmus paper blue. And the reason for that? Bases release hydroxide, or OH- ions. So it's basically this ultimate showdown of H+ versus OH-. Now, you might be wondering, how do we actually know which is which without, taste testing potentially dangerous chemicals? Well, that's exactly where indicators come in. Think of indicators as our little chemical detectives. They're substances that literally change color when exposed to different types of acidic or basic environments. So they give us a really clear visual clue about the invisible chemical nature of a substance, absolutely no taste testing required. We can also categorize these acids based on where they actually come from. Mineral acids are derived from the Earth's minerals, stuff like sulfuric, nitric, and hydrochloric acid. These are the heavy hitters. But on the other hand, we have organic acids. These are naturally derived from plants and animals. We're talking about the citric acid in your morning orange juice, ascorbic acid, tartaric acid, basically the stuff you're going to find right there in your fridge or pantry.
All right, moving right along to Section 2, Strength, Concentration, and pH.
Okay, let's actually slow down for a second here, because there's a really crucial process we need to understand called ionization. This is pretty much the engine of everything we're discussing today. Ionization is just the process of forming ions in an aqueous solution. To put it simply, when you mix these molecules with water, they break apart, or dissociate, into charged particles called ions. And that specific dissociation is exactly what makes them so active and reactive in the first place. And this ionization process directly dictates an acid's strength. Strong acids, they undergo complete ionization. Basically, every single molecule breaks apart. Chemists actually represent this total commitment with a single arrowhead in their formulas. Hydrochloric acid, or HCl, is a perfect example of this. Weak acids, however, like acetic acid, only undergo incomplete ionization, so only some of the molecules break apart, and we show this sort of chemical hesitation with a double arrowhead. Now, one quick thing, don't confuse strength with concentration. They're totally different concepts. An acid's concentration is purely about its ratio to water. A concentrated acid has the absolute minimum amount of water possible. It's just packed tightly with acid molecules. A dilute acid, on the other hand, has a maximum amount of water. So you could actually have a strong acid that is highly diluted or a weak acid that is highly concentrated. It's really just a matter of how much water is in the mix. So, how do we measure all this hydrogen ion concentration? We use the pH scale. And to really grasp the pH scale, we have to start dead center at the number 7. In the chemistry world, a pH of exactly 7 represents perfect neutrality. It is the absolute perfect balance point where a substance is neither acidic nor basic. From that neutral 7, the scale builds out into a full spectrum. Technically, the pH scale is a negative logarithm of hydrogen ion concentration. I know that sounds super complicated, but here is what you actually need to take away from this. On the lower end, from 1 to 6, we have our acids. The lower the number, the higher the hydrogen concentration, so a pH of 1 is highly, highly acidic. Then we hit our neutral 7, and as we climb from 8 all the way up to 14, the substances become increasingly basic in nature. Which brings us to Section 3, the power of reactions. This all raises a really fascinating question. What actually happens when these opposite chemical forces finally meet? Like when the high hydrogen ion energy of an acid just crashes into the hydroxide power of a base, who actually wins the chemical tug of war?
Well, surprise, nobody wins. They compromise. We call this neutralization. It's a reaction where an acid and a base completely neutralize each other. They totally cancel out their extreme properties to form something entirely new and generally pretty harmless, a salt. Oh, and they also release water in the process. It's basically the ultimate chemical truce. And the coolest part is that chemistry is wonderfully predictable once you know the recipes. For instance, if you mix a metal with dilute hydrochloric acid, you're going to get a salt and release hydrogen gas. What if you mix an acid with a carbonate? Well, you get a salt, water, and carbon dioxide gas. And an acid plus a metal oxide, that yields salt and water. These equations are amazing because they show us exactly how matter transforms when acids go to work. Let's bring this all home with Section 4, Everyday Salts and Compounds. There are actually 5 major everyday salts that are born straight from the reactions we were just talking about. First up, we have common salt, or sodium chloride, NaCl. That's literally the stuff you sprinkle on your French fries, and it's formed by neutralizing hydrochloric acid with sodium hydroxide. Then there's washing soda, sodium carbonate decahydrate, which is used in laundry and making glass. Next is baking soda, sodium hydrogen carbonate, or NaHCO3. That's the exact chemical that makes the cake in your kitchen rise. We also have bleaching powder, and finally, plaster of Paris. I do want to highlight something really cool about that common salt, though. It's not just for seasoning your food. It's actually a foundational building block for massive industrial manufacturing. Through something called the chloroalkali process, factories mix sodium chloride with water and use electrolysis to manufacture sodium hydroxide. And in doing so, they release highly valuable hydrogen and chlorine gas. So yeah, your basic table salt is an absolute chemical powerhouse.
And what exactly happens to that chlorine gas? Well, that leads us right to bleaching powder, or calcium oxychloride. It's manufactured in these massive facilities called Hausenklever or Bachmann plants by combining slaked slime with chlorine. We rely on this compound constantly for disinfecting our drinking water, bleaching cotton in the textile industry, and, get this, it's incredibly even used to make wool unshrinkable. How cool is that? Finally, let's take a quick look at plaster of Paris, or calcium sulfate hemihydrate. You get this by heating a mineral called gypsum to 373 Kelvin. But here's a fun little trivia fact for you. Why on earth is it called plaster of Paris? Well, simply because the gypsum it's derived from is found predominantly in Paris. It's a completely essential compound used by doctors for plastering fractured bones, making decorative items, and even crafting the chalk used on blackboards.
So as we wrap up this explainer, I want to leave you with a question to ponder. The next time you're washing your clothes, or baking a delicious cake, or even just tasting something sharply sour, will you be able to see the invisible chemical tug-of-war happening right in front of you? Because once you really understand this hidden balance of acids, bases, and salts, you realize that chemistry isn't just something stuck in a textbook. It is literally the very fabric of our everyday lives. Keep learning, keep exploring, and I'll catch you on the next one.